All right, I think we can get started. So, welcome to the second talk from the afternoon session. So, it's my great pleasure to have with us Sze-Man Ngai, and he's going to talk to us about the spectral theory of Krein-Feller operators rising in fractal geometry. So, let's welcome him.
Thank you very much for the introduction. I would like to thank the organizers for giving me this opportunity to give a talk in this congress. Most of the recent work is joined with Leo Yang and Wenchen Zhao at Hunan Normal University. Let me start with this classical result by Weil. So delta denotes the dilution Laplacian on a bounded domain omega in Rn with smooth boundary. Lambda k are the eigenvalues of the negative of the Laplacian, and n lambda is the negative Laplacian is the eigenvalue counting function. So it's the number of eigenvalues less than or equal to lambda. So Weil proved the following law, n lambda is given by this leading term. This is a crucial part, lambda to the n over 2. Okay. Oh, of course, this part is also important, but we're interested in this. Okay, and this part. Okay, but for fractal Laplacians, that I'm going to explain later. Right, so here omega n is the volume of the unit volume Rn, and a similar formula holds on a compact Riemannian manifold. So Weil's proof uses variational method and depends on knowing the eigenvalues of Laplacian non-rectangles. Proof on a manifold relies on heat kernel estimate and Tauberian theory. These are standard methods. Of course, I know that there are other methods, but for fractal sets, these methods, standard methods, usually cannot be applied. So let me start with a fractal. This is the well-known Sierpinski gasket. So you take an equilateral triangle, remove the middle fourth. Okay, so we're left with these three, and then continue this process. In each of these three triangles, remove the middle one. Okay, so this is a decreasing sequence of compact, non-empty compact subsets. We know that the intersection is non-empty, and the intersection is the Sierpinski gasket. This is way to generate fractal, but there's a more general way to generate fractal sets, which I will explain first. Okay, so fractal sets are usually generated by iterated function systems. So an iterated function system on Rn is just a finite family of contractions, okay, that we call Si. Okay, so given any finite family of contractions, okay, it is known that there exists a unique non-empty compact set F called the attractor, such that F is the union of copies of itself under these contractions. So F is the union of SIFs. Okay. All right, so this is the fractal that we're interested in. Um, uh, in fractal geometry. This is one way, of course, this is one way of generating fractals. If the contractions are similitudes, then we call F a self-similar set. If the contractions are conformal mappings, then we say F is a conformal set or self-conformal set. Okay. All right, so besides generating a fractal set, we can use an iterated function system along with a set of probability weights to generate a measure supported on the fractal set. It's done this way. So you take a set of probability weights. So the sum of the PIs is equal to 1. The PIs are positive. Okay. then it's known that there exists a unique probability measure mu called an invariant measure, satisfying such a self-similar identity. Okay. And moreover, the support of mu is equal to f. Okay, so I'm going to explain this identity in a moment by using the Shabinski gasket. Okay, so again, if the contractions are similitudes, we call mu a self-similar mesh. If the contractions are conformal mappings, then we call mu a self-conformal mesh or conformal mesh. So let me explain. Okay, so now to generate the Shabinski gasket, we can use an iterated function system. Say for example, the iterated function system I choose consists of three similarities, okay, contractions S1, S2, and S3. And then you repeat this. You take compositions as say S2, S1 takes to here. Okay, so this is first level of iteration. Second level of iteration consisting of images under these under the compositions of the maps. Okay. And so the set F is the limit of this sequence of sets. To see how the probability measure mu is generated, the invariant measure is generated, you can just, as an example, say put weight P1, P2, P3. So you assign a weight to S1, P1 to S1, P2 to S2, P3 to S3. Okay, so the measure of this say this interval, this triangle, it's associated with S2, S1. So put the weight P2, P1, and so this way you get a probability measure supported on the Shabinski gasket. All right, so for the Shabinski gasket, okay, this is a result by Kigami and Lapidus. So there's a Laplacian defined on this Shabinski gasket. So there's an analytical way of defining this Laplacian. Was first defined by Kigami by using graphs, first defining the Laplacians and graphs, and then take the limit, the scale limit. All right, so for this Laplacian, the eigenvalue counting function. So while law takes this this form, not exactly the while law, but it tells us that the number of the eigenvalue counting function grows like lambda to the 2s, ds over 2. Okay. ds over 2 instead of n over 2 as in the while law. So this number is important. I'll convince you that this is an important quantity called the spectral dimension. Now, for the Shabinski gasket with equal weights, so we put 1/3, 1/3, 1/3. This ds is approximately 1.36. The method that they use is renewal theorem, and renewal theorem is perhaps the most fruitful method for obtaining wild asymptotics in fractal geometry. So, the renewal theorem says that if a function f, we can write f as the convolution of f with some probability measure plus some error. So some error term. This is some error. And if the error decays sufficiently fast to 0, then f either tends to a non-zero constant, or f is a non-zero periodic function. or multiplicatively periodic function. So for fractal sets, renewal theorem is probably the most useful method in getting asymptotic behaviors. Okay. All right, so now I want to explain the class of fractal sets that I'm going to mention in my talk. Okay. Now, for iterative function systems, there's a very important condition. It's called the open set condition. Okay. So given an iterative function system, which as I said is just a finite family of contractions, okay, if there exists a non-empty bounded open set U, okay, such that U is invariant under the maps Si, and here's a separation condition. The images of U under Si and Sj are disjoint for I not equal to J, separation condition. Then we say that the open set condition is satisfied. Okay, it's important because if the Si are similarities, then by a result by a theorem of Hutchinson, if the open set condition is satisfied, then the Hausdorff dimension of the self-similar set can be computed by a simple formula. So the Shapinsky gasket is generated by an iterative function system that satisfies the open set condition. So the iterative function system that we used in the previous example, the same iterative function system, satisfies the open set condition. If we take the interior of this triangle, then S1, S2, S3 sends it to these three pieces. Okay, the interiors are disjoint. Okay, and of this invariant lies inside the triangle. Each of them lies in the triangle. Okay, so this condition is important, but there are also fractal sets or fractal measures that do not satisfy the open set condition, and they're also important. In fact, these are the fractal sets and fractal measures that I'm more interested in because they are less known. Okay? But they are also important. So here's an example of an iterative function system that does not satisfy the open set condition. And in this case, we say that they have overlaps. The iterative function systems have overlaps. Okay. So here's a very simple, iterative function system. Well, I said iterative function system. This is simple. So we only take two maps. Okay, each is a contractive similar to. So R is the contraction ratio. So take S1 just strings, and then just strings by a factor R, contracts by a factor R, and S2 contracts and then translates. Let's assume that the contraction ratio is between 1/2 and 1. Okay, and so by the general theory, this iterative function system, along with any set of probability weights, will generate a measure. Okay, so take the simplest probability weight, 1/2, 1/2. Okay, so the self-similar measure generated satisfies this identity. Okay, and this identity just reflects the way that you distribute the weights, 1/2, 1/2, 1/2. Okay, all right. So mu R is called an infinite Bernoulli convolution. Okay, the iterative function system in fractals we view it this way. We restrict this if we restrict the domain to 0, 1, then S1 sends the unit envelope to here, S2 sends the unit envelope to here. Okay. Now, this class of measures is interesting because they have been studied for a long time and it's not completely understood. Okay, so let me just mention one result. Okay, This proof 1939 that if the contraction ratio R is the reciprocal is of a Peso number. So the reciprocal of R is a Peso number, which is an algebraic integer greater than 1, whose algebraic conjugates all lie strictly inside the unit disk. Um, then mu R is singular. Okay. And another important result proved by Boris Solomyak is that mu R is absolutely continuous with respect to Lebesgue measure for almost all R between 1/2 and 1. By the way, if R is less than 1/2, then it's singular. It's Kendall type measure. And there are other landmark results by Paris Schlag, Hoffman, Schmerken, and Value. Um, yeah, Yuval Paris. Yeah, he worked on this problem. Yeah. But it is still open, while open whether or for which R mu R is absolutely continuous. Okay, so this family proved by others is the only known family for which mm, mm, mu R is known to be single. So the best result now is that if um, uh, let's say phrase it this way, if R is transcendental, then it cannot be single. All right, so has been studied for a long time. So now, so self-similar measures that do not satisfy the open set condition with overlaps are measures that we're interested in. But how about Laplace? Okay, so Kimami was able to define Laplace on certain fractal sets called post-critically finite. So these are the fractals connected, but if you remove a finite number of points, then it becomes disconnected. Okay. Now, for the class of infinite Bernoulli convolutions that I mentioned, they do not satisfy this condition. And so, but can we still study these the analytic properties of this measure? So can we study like wave equation, head equation defined on this on this fractal sets? Okay. Well, that's the fractal sets it's trivial in this case. It's just 0, 1, but the measure is complicated. Okay. All right. So this is general framework to define the Laplacian. This is not it's not new, but let me phrase it this way. Omega is bounded open set. Okay. Mu is a positive finite Fourier measure. We need a Poincare inequality for measures. So there's a constant C, positive, so that this inequality holds for all continuous functions with compact support. This, if we change this mu to x, then it's the Poincare inequality. Okay, so if this inequality holds, then we can define a non-negative self-adjoint operator associated with this closed form. Okay, this is a standard Dirichlet form. Okay, but the L2 space is different. Okay, so this is called the Krein-Feller operator or Dirichlet Laplacian defined by mu. Okay, we're interested in the case where mu is a fractal measure. All right, so now we have this Laplacian that defined on a domain, and this and it depends on the measure. Okay, so this for say the unit interval and the four measures that we mentioned before, this Laplacian is I think it's a Laplacian, right? Laplacian that describes how a wave propagates and how heat diffuses on this unit envelope. And problem was studied by Krein-Feller a long time ago in the 50s. Okay, so we are interested in the spectral problem. So eigenvalue asymptotics. So first of all, let's make sure that there exists as a, a orthonormal basis of eigenfunctions. Okay, so based mainly on the result of Marcia, we obtain this result. Okay, so that's that if L infinity dimension of a measure is greater than n minus 2, okay, then we get the Poincare inequality, and there exists an orthonormal basis of eigenfunctions of this Krein-Feller operator, and the eigenvalues increase to infinity. The eigenspaces are finite dimensional. And so this quantity, okay, L infinite dimension.
This is like for the Dirichlet problem, right? The eigenvalue problem for
Yeah,
the Dirichlet.
that is a Dirichlet problem.
Dirichlet problem.
Dirichlet problem, yeah. Yes.
For the new Laplacian. But what about the Neumann problem? Do you expect something?
Yeah, for one dimension, it's almost similar. So, but higher dimensions, it's some result. This quantity called the lower L infinity dimension arises in we study multifractal properties of fractal measures, and it's defined as follows: L infinity dimensions lim n of the log of sup of mu b delta x. Okay, so you want you want to take the bar, you measure an R bar, and you want to see its R to what experiment here. This is the you want to sup. Okay, you want to take the sup, so the heaviest point. Okay, heaviest point. Okay, so you take the take log on both sides and divide by log delta. So I use delta. Should use delta instead of R. Sorry. Okay, now we have the sequence of eigenfunctions. We can define the eigenvalue counting function as usual. Okay, n lambda is the number of eigenvalues less than or equal to lambda. Okay. And we can define the spectral dimension as well, this is spectral dimension, okay, n lambda over log, the log n lambda over log lambda. Okay, so this tells us how to well, how n lambda grows, lambda to the how. And in the wild law, it's n over 2. Okay, n over 2. Okay, so for if for this fractal Laplacian, we want to see what over 2. Okay, the what over 2, and so there's a 2 here. Okay, so this ds is what we call is called the spectral dimension. Okay, so for standard Cantor measure on 0, 1 is just an example. You can compute it. All right, so I'll explain why we're interested in this spectral dimension. So as usual, if the open set condition is satisfied, then the fractal sets have simpler structures, and the iterations are much more tractable. And so this is a result proof about 30 years ago by Naimak and Michael Solomiak. They proved that the spectral dimension is given by this under some assumptions. So we have an iterated function system, contractive similitude. So we have self-similar set, self-similar measure, open set condition satisfied. This given by this pi the probability weights or other contractions of the similitudes. Okay. So the spectral dimension is given by this simple formula. Okay. So question is, what if we don't have the open set condition? So I was able to compute. This was work done quite a long time ago for the infinite Bernoulli convolution associated with the golden ratio. Okay, and there's another family of fractal measures. Okay, I was able to compute the spectral dimension. ds to alpha. Alpha is the unique positive real number satisfying. That's such a complicated equation. Okay, so I will briefly tell you what the CJ are probably on the board in a moment. So it's just some formula. We know we can compute the spectral dimension, but it's much more complicated without the open set condition. Similar results are obtained for convolutions of Cantor type measures. And technique we use second order identities and vector value renewal theorem. So again, renewal theorem, but not the original form. But we need a vector form of renewal theorems. Okay. So quickly, the main idea here is so this is the idea by Robert Strickhatz. So for the infinite Bernoulli convolution associated with the golden ratio, the golden ratio is root of is a Poisson number. Is the root of this equation. If this is actually the reciprocal, it's square root 5 minus 1 over 2, approximately. All right, so this is a contraction ratio, about 0.6. Okay. So Strickhatz has a nice idea that enable us to compute the measures of exact measures of these intervals. So actually, all we need is to consider this part. Okay, so if we magnify this part, then using so-called second order identities, one can compute the exact measure of, say, there's a part in the middle, and like these. So there's a sequence of subintervals, okay, with length converging to 0, and they actually fill up these intervals, fill up this part, okay, and for each of this interval, there's a way to compute the measure of mu, okay, the mu measure of the interval by using a matrix product, and those are the measures are given by CJ. Okay, so this is the only, unfortunately, this is the only Poisson number for which the measure can be computed this way, unfortunately. So for the other Poisson numbers, we don't know whether, well, we don't have a way to compute the measure this way. Okay. So for this particular infinite Bernoulli convolution, even though it does not satisfy the open set condition, we still know quite a lot because of this idea, second order identity. So we're able to compute this, but there are other measures like convolution for Cantor measures that have the same property. So same technique can be applied. Excuse me. Since then, let me back up a little bit. So since this work, a lot of work have been done to compute spectral dimensions of various measures. But I don't have time to mention additional work. Okay. So I just want to mention one particular interesting result. Okay. So by Kessler, Berman, Niemann, recent preprint, they proved that for self-conformal measures, the spectral dimension can be obtained by from another quantity called the LQ spectrum, which is a very important function that arises in the multifractal decomposition of meshes. So it's some some function, um, some very important function characterized um, used to study the multifractal property of meshes. Okay, so you take the sum of a pack disjoint bars with center at supported measure raised to the power q and take the sum. So um, some important function. It's a concave function giving us a lot of information. It gives us the L infinity dimension. If you let q tend to infinity, is the L infinity dimension is the asymptotic slope. So so their theorem says that we can get the spectral dimension if we can compute this. Okay, so and a lot of work was or have been done before the result to compute tau q dimension, the tau q spectrum. All right, so that's what I want to say about the computation of LQ spectrum. Sorry, the dimension, LQ, spectral dimension. Some applications, and why are we interested in the LQ, the spectral dimension? Okay, so this is joint work with Qing Hu, Jiaxin Hu. So using the spectral dimension, the spectral dimension, and properties of the measure, the measure that we know, we're able to get two-sided heat kernel estimates for the Laplacian, and it turns out that as for this is common for fractals, heat kernel estimate is sub-Gaussian. Okay, so it means this exponent here, it's one. This exponent is one for Rn, and for Laplacian Rn, standard Laplacian R or Laplacian compared with Riemannian manifolds. Okay, but for fractals, this is less than one. So the motivation for doing this was because there's a conjecture by Strickhaus. Okay, so Strickhaus et al. Conjecture that waves may propagate with infinite speed on certain fractals. Okay, and intactly proved this conjecture for PCF fractals. So that includes the gas. For iterated function systems that do not satisfy the open set condition, like the infinite Bernoulli convolution that we mentioned, the PCF condition does not hold. Okay, but the least proof is quite robust, and we can easily extend this theorem to include iterated function systems with overlaps. Okay, so using this and the sub-Gaussian heat kernel estimate, we can prove that the wave propagates with infinite speed on the unit interval. Okay, if we use this Laplacian, the Laplacian defined by the infinite Bernoulli convolution associated with the golden ratio. All right, so that's what I want to say about this background material. Any questions so far before we move to the? All right, so I want to mention to join work with more recent, a couple of years already, with Lei Ouyang and Wenchen Zhao. Okay, so we want to extend the theory to Riemannian manifolds. Okay, first of all, there are some motivations. You can construct lots of interesting fractals. In fact, on Riemannian manifolds, this is cylinder. This is the flat torus. So this is a sphere. This looks like PCF. It looks like well-known fractal set called V-check set on iron. And this is a Stravinsky gasket with overlaps. So they present in challenging problems. Even like something like this is it's hard for us, to compute even the box dimension. But we have some results concerning the house of dimension of these fractal sets, and partial results on the box dimension of some of these fractal sets. Okay. But here's the main motivation is the Yau's conjecture concerning nodal sets of eigen functions. Okay, nodal sets of eigenfunctions. So Yau's conjecture that on I think it's compact Riemannian manifold, the nodal sets or the zero set of the eigenfunctions satisfy these bounds. Okay. This is house of measure, n minus one dimensional house of measure of the nodal set, the zero set of eigenfunction u, and this is the corresponding eigen value lambda. So that's the conjecture. The lower bound was proved by Lagunov. Upper bound is still open. Okay. So I gave this talk in 2016, and Professor Yao asked me how the nodal sets of the he actually asked me how the eigenfunctions behave. How the zeros of eigenfunction behave. I didn't know. I only know the one dimensional case at the time. And then he told me about this conjecture, and also Lagunov was visiting him. Gave a couple of talks. So I became interested in this problem. And I think for the fractal case, we'll have to adjust the Yau's conjecture to this form. Okay, so it's ds is a spectral dimension, ds over 2n. Okay, this is true in one dimension, and it's not hard. It's very easy to see. Okay, but I don't have any result for higher dimensions. But this is our motivation. So to first to be able to study this problem, we need to make sure that we have a complete orthonormal base of eigenfunctions. Okay, and we also need to make sure that the eigenfunctions are continuous. Otherwise, the zero sets are not well defined. So that's the two questions we need to solve. But for today's talk, I will talk about a slightly more general setting, because the setting for functions was I reported before, and so I want to talk about the whole Hodge theorem that guarantees that there exists an orthonormal basis of eigenfunctions, not just on zero forms, but on K forms. Okay, so this is more technical notation. So again, we have a smooth. Well, for this, for compact Riemannian manifolds, a smooth M is a compact Riemannian manifold. For non-compact manifolds with other results, but I'm not going to talk about them. Mu is a measure supported on omega bar. It's a subset of M, and these are the space of smooth K forms. So in the Hodge theory, you have the exterior derivative D and the co-differential, the adjoint D star, and the Laplacian D1 star D1 star D0. This is Laplacian and zero forms. Laplacian and K forms are given by the sum of these two terms. Okay. So I have Hodge Laplacian, and we need conditions just like the Poincare inequality we mentioned. So we divide this into two cases. One is with a non-empty boundary, usually boundary condition, and there's a zero boundary, empty boundary condition. Empty boundary condition. So so this is a kind of Poincare inequality that I mentioned earlier. For the empty boundary condition, there's an extra term because of constants, constant functions. If if we put constant functions, then it would be zero here and non-zero here. Okay, so by assuming these Poincare conditions, we can define a Laplacian form just like before. Define Laplacian on K forms. Okay, with respect to different boundary conditions. All right, so we have Laplacian transforms. So the main result here is again, suppose the infinite dimension mu is greater than n minus 2, then there exists an orthonormal basis of L2 consisting of eigenforms, and the eigenvalues are satisfied. The eigenvalues tend to infinity. Okay, so again with this condition, L infinite dimension is greater than n minus 2. Okay. This is important condition even in Rn. So it just the result could be false if we do not false if we do not assume this condition. Okay, so all right, so for the remaining like 12 minutes, I will give an outline of proof of this result only for the case that only for the function case, the zero form case, because the idea is quite similar. All right, so main ingredients of the proof, how to prove that there exists an orthonormal basis of eigenfunctions. So again, just like in Rn, we use a result of Marzius, but result of Marzius is for Rn only. So we need to generalize his result to Riemannian manifolds. So this is a generalization. Okay, so let M be a compact Riemannian manifold. Okay. Mu as before. If Q is greater than 2, then the unit bar is relatively compact in LQ in this space of forms with a measure mu, if and only if we have these local density properties. Okay. So it's very hard to verify. This condition is it's not easy to verify. I don't know how to verify such a condition. Okay. So we use L infinite dimension greater than equal to as a sufficient condition to guarantee this. Okay, but this is the main theorem, the difficult part. Okay, so if the unit bar, I have to say that more carefully. Okay, so this unit bar is a unit bar of smooth in the space of smooth functions with compact support. So once we can prove that the unit bar of I think smooth functions with compact support is relatively compact in this space. Okay. Okay. Then we know that there exists a standard result that says that there exists an orthonormal base of eigenfunctions. Okay. So this compactness of embedding is the most technical part. Okay. But how do we get compactness of embedding? So we use masses result on Rn. So we need to preserve this local um, density properties when we move from manifold to Euclidean space. Okay, so we construct normal coordinate charts. Okay, that maps from uh, manifold to Rn. Okay, and we, and we use these charts to induce a mesh on Euclidean space Rn. Okay, and then if we can prove that the local density properties are preserved, then we get compactness of embedding by using uh, Marx's theorem, and then we transfer the result back to manifolds. So that's the rough idea. Okay, so but when we use this local this um, normal coordinate chart to pull the Riemannian manifold uh, Euclidean space, okay, and back. Um, so the bars will be could be distorted, okay. So we have to somehow control the distortion of the bars, okay, of the sets, okay, because the size of the sets could change the mesh, okay. So so we use comparison theorems, okay, to to um, to guarantee to prove that the distortion can be controlled. Okay, and so we use the Tobanogov theorem and Rauch comparison theorem. Okay, so this requires that we bound uh, the sectional curvature. Okay, so bound the sectional curvature away from. This requires that the sectional curvature is bounded below and above by positive by real numbers. Okay, and this is possible because we're we're talking about compact sets. Okay, so let me show you the figure. So one of these is in Euclidean space, okay, Euclidean bar. This is Euclidean bar. This is one on Riemannian manifold. And actually, these sets are what we use to compare volumes. Okay, these are so this slice here is distorted by the normal coordinate charts. Okay, to control the distortion, these are the geodesics. Okay, geodesics are preserved, okay, by this normal coordinate charts. Okay, but to control the distortion, we have to make sure that the geodesics do not diverge too fast or do not converge too fast. And Kobayanov's theorem um, uh, guarantees that the if the sectional curvature has low sectional curvatures have a lower bound, then the geodesics do not diverge too fast. And Rauch's comparison theorem guarantees that if the sectional curvatures are upper bound, then the geodesics do not converge too fast. Okay, so these spots, this region will not get infinite too big or too small. Okay, and so but since I said it's compact, this we don't have to assume that they are automatically fulfilled. And so that was the idea of the proof of the very, very rough idea of the proof of the embedding theorem. Once we have the embedding, then there exists all the normal basis of eigenfunctions. Then we can talk about we can define spectral dimension. And so finally, about continuity of eigenfunctions. This is joined with Wen-Chen Zhao. So the eigenfunctions that we got from the Hart theorem are actually continuous. Okay, so actually we just have to assume this condition. L infinite dimension greater than n minus 2, then we know that there exists eigenfunctions, and this result ensures that the eigenfunction is continuous. So we can we can then talk about the we can talk about the generalization of Gauss conjecture to include these measures, okay, to include these Laplacians, okay, and if mu if you choose mu to be to be Lebesgue measure or to the Riemannian volume measure, then this this Laplacian coincides with the classical Laplacian. All right, so this is my last page. So the proof of this is not that hard. So first, we use the defined Green's function, and then we will show that the Green's this Green's operator, sorry, Green's operator. This is Green's function. Will show that the Green's operator is kind of inverse of the Laplacian. So, but it's not exactly the inverse of the Laplacian. We have to restrict this to suitable domains. Okay, so the suitable domain is H mu tilde. Okay, so these are all the functions that are orthogonal to constant functions. So we mod out the constant functions. So this includes all the eigenfunctions associated with non-zero eigenvalues. Okay. Actually, strictly positive eigenvalues. So using this inverse relation, we can prove that lambda is an eigenfunction of the mu Laplacian if and only if it satisfies this u is equal to lambda g mu u plus c. Okay, and so if u is an eigenfunctions, and we can prove that this is continuous, then u will be continuous. So now it reduces to prove that g mu u is continuous. Okay, this can be done with some small effort. Okay, all right. So let me stop here. Thank you very much.
If there are any questions, please.
Thank you. So I guess I could probably put my question within the Rn setting, like, um, I guess one question is when you define, like, consider the Dirichlet form, um, is there a particular reason you want to integrate with respect to the Beck measure instead of the mu measure you're considering?
Yes. So when we derive this Laplacian on the unit interval, we're thinking of the wave equation. Okay, so we use Newton's second law, and so Newton's second law says force equals mass times acceleration. So we have to use dx, the Beck measure. So instead of d mu on both sides, we have dx and d mu. So this Laplacian then would describe the the wave equation if we have a string and when it's plugged. And when we derive the heat equation, is also is dx on the other side. So of course you can actually people study this for general measure or use both mu on both sides. And I think in Gregorian's work he used mu on both sides. So it's just different Laplacian. So because the main reason is we we started to work on wave equation and heat equation. Think this dx is the right one, but it's actually a Strickert posed this problem for us, and that's what he set up for us with the dx.
So for this choice of ds, if you try to write down what the corresponding Laplacian is, I guess I was trying to do it in my head. to do like integration by parts, starting from your gradient square dx to get the Laplacian. It seems like you just have 1 over mu, then the classical Laplacian.
Yeah. It's
Oh,
one of
okay.
it's like one of the mu. So one of the results is let me see if I can write it down correctly. Mu Laplacian of u equal to f if and only if the regular Laplacian of u is f d mu. That's it. And if you think of if if I don't know if mu is absolutely continuous g dx, then I mean yeah. Um, then you probably had division something like that. I forgot exactly, but yeah, mu Laplacian of u is f if and only if regular Laplacian of u is f d mu in the sense of distribution. Okay, and yeah, I actually derived it before. Yeah, you're right. You um,
Yeah, I guess it was when Cesar was asking about the Neumann Dirichlet condition. I was thinking about whether it's simple to define what the Neumann condition
oh
is in this case. I guess it seems
yeah,
fine.
Neumann you have to assume some smoothness boundary condition boundary. So here you don't have to worry about the boundary, but for Neumann, I think you have to make assumptions on the boundary. Extension property.
Oh, and another thing, quick thing is, do you use like, because in the classical case we consider often like smooth functions with complex support, those kind of things as our nice functions to use. So in this case, do you have functions that play a similar role? Or?
Yeah. We actually use the so H01 H0 H0 space. When we talk about Dirichlet boundary conditions, we use compact infinity functions with compact support, right? So the Poincare inequality dimension start with infinity function with compact support. Otherwise, it's not defined. Uh, so and so yeah, we use that to define Poincare inequality, and and um, and we define the domain of this Laplacian. We have to embed H0, this H0 space, which is the which is completion of this of C infinity function with complex support, right? So the Poincare inequality allows us to embed this into L2 mu space. So that's how we use C infinity functions.
Oh, I guess I'm just reminded. Maybe in the previous question, maybe it's hard to define gradient in terms of the mu measure.
Yeah. That's an interesting question. Yeah, that's a question that I been thinking about for a long time, but it's so far. It would be nice if we can define the gradient with that mu. I hope there's a way to, but I haven't worked really hard on it. But we've always asked this question whether there's a mu gradient. Yeah, in this setting, this context. That's a very interesting question.
Thank you for the very nice.
You're welcome.
Other questions, please. Other questions? No questions? Well, I have a question. So when you define this new Laplacian, and you've talked about the Wales law, so there is this asymptotic, there is a conjecture by Wales, you know, the asymptotic estimates for the k eigenvalue. It was proven by Peterlee and Yao back in the 80s that they have an average. They prove this conjecture in the average sense. So they look at the average mean of the eigenvalues. Is there something similar for this kind of Laplacian? for the with Dirichlet.
Yeah.
Do you know
I
the
know
paper?
I know paper by Lee and Yao about the sums of eigenvalues.
Yes,
But
yes,
yeah,
exactly.
sum of
Lee
eigenvalues.
and Lee Yao
Lee
inequality.
Yao, yes.
Do we
For
have
the
something like this in this?
yeah, actually, with this some like generalization of result to the RN, but not as nice
You
generalizations.
see, because that's an inequality there. They have an inequality,
Yeah,
greater or equal, not nothing as.
yes, I remember. So I did some generalization of the result, but our results not as nice in the sense that the our bounds in terms of the complicated one is not as nice as the results. So yes, I was thinking it would be interesting to
Okay,
get
so
better.
it's not known. Okay. Okay. Other questions, please. Well, if there are no other questions, let's thank our speaker again.